right, so I'm going to be real quick. So Sheng gave a really nice introduction to shear thickening, or shear thinning in suspensions, but he left off what I would call the most interesting part, the shear thickening behavior. And this was something, unlike shear thinning, this is much more controversial, still controversial a bit today. And this is an area where granular physics is really, ideas taken from granular physics really helped us get a handle on that problem. So if you haven't seen shear thickening suspensions before, you can probably go down in Heinrich's lab and find someone who can show you some cornstarch and water. But if you're not familiar, it's a lot of fun to make in your home, make in your kitchen, make a big mess. And you can see they're poking it. If they poke it gently, it behaves like a liquid. But if they poke it too hard or stir too fast, it suddenly becomes much more viscous, almost solid-like. And this is something that, despite the fact that it's so easy to observe, there's nothing magic about cornstarch. This shear thickening is a ubiquitous phenomena in dense suspensions of hard particles. So that makes it really important for a lot of industrial processes. But despite the fact that it's so easy to observe and so ubiquitous, there's been a lot of debate about what's actually causing this phenomenon. For a while, the default explanation focused on the hydrodynamic interactions between the particles, particularly these large lubrication forces that could build up as when you pushed two particles close together. However, this has been controversial. Prior to that, there was this idea that was related to an order-disorder transition, and there were lots of shade thrown around in articles about what was the dominant mechanism. Though, at least for a while, that hydrocluster hydrodynamic view was the dominant view. However, in simulations with only these hydrodynamic interactions, only these lubrication forces, they can only get very mild shear thickening. Maybe a factor of 2 or so over orders of magnitude in shear rate. Whereas in experiments, they tended to see stuff that looked very different. So this is some type of shear thickening suspension. These are, you tend to find very general types of features where there's the shear thinning, the second Newtonian plateau that you heard about before, and then this shear thickening. And you can see up here, at some point, the shear thickening is so dramatic that the viscosity is just increasing like a vertical line, meaning that your stress, you're flowing at the same shear rate as your stress is ramping up higher and higher. So it seems like there's a real discrepancy between what people were seeing with just these hydrodynamics and experiments. So they're motivated by this. There was a lot of work sort of started by people here in Chicago, Eric Brown and Heinrich Jaeger, trying to look at the shear thickening suspensions through a new view to understand what was missing. There are a lot of sort of different approaches that people were taking. I'm going to be talking about one that really focuses on this idea that you need frictional contact between your particles to get this shear thickening behavior. So just to highlight some generic features of shear thickening suspensions, you typically see that you have for a typical shear thickening suspension, this happens to be silica in glycerol and water. You see this is the second Newtonian plateau. So I'm starting up to the shear thinning that Sheng talked about was somewhere back here. I'm starting at the second Newtonian plateau, and then you see this shear thickening. And then you tend to reach this or yet again, another plateau. I call it eta STS because it's your shear thickened plateau. And this other shear thickened plateau increases with the concentration of your particles. But you can see that independent of concentration of your particles, the shear thickening begins at a characteristic onset stress. Here it's somewhere around 100 pascals or so. If you plot these two different plateau values, the second Newtonian plateau, so this sort of high shear plateau, and then your shear thickened plateau viscosity. For all different types of shear thickening suspensions, you tend to find that you get sort of this two-branch structure. So if you look at this Newtonian plateau here, you have this viscosity increasing with the volume fraction, with the concentration of your particles, and then it diverges, looks like it's diverging around 60-some%. So this is very close to what you might expect around random close packing for hard spheres. So it's easy to sort of get a handle on, or think about why the viscosity is diverging here. But this shear thickened plateau is diverging earlier at a lower volume fraction, somewhere around 55 or 56%. So this is very reminiscent of a scenario we have in granular materials. If you have frictionless hard spheres, they will jam around what they call random close packing, something around 64%, depending on the details of how you prepared them. But if you have friction between your particles, you can stabilize stable packings at much lower packing densities, down to what you call random loose packing, which depends on the friction coefficient between your particles. And another way to sort of approach this is if you have, you can also think of this in terms of a sort of shear jamming perspective, where again, if you have finite friction coefficient between your particles, there are you can, in addition to your sort of normal jamming point, there are these, you can get into shear jammed configurations that, as you under shear due to the finite friction between your particles. So motivated by these ideas, people started adding static friction into their this sort of Stokesian dynamic simulations. And lo and behold, when they added friction, added it in a particular way so that you turn on friction under increasing stress, lo and behold, they were able to reproduce this sort of two-branch or two-plateau structure that people saw in the experiments. And if they plot these two different these viscosity plateaus and the volume fraction, you see the two different branches that I showed you earlier. This lubricated or frictionless branch, and then this upper shear thickened or frictional branch that depends exactly on the coefficient of friction between your particles. And then you can understand how your shear thickening, you're moving from one branch to the other as you're increasing the shear stress and increasing the fraction of frictional contacts. So there's been a lot of work exploring different avenues of this friction-based scenario over recent years. And the thing that really I think is important to highlight about this is that you have to get away from viewing your particles just as simple hard spheres. You have to think about the details of what happens when they come into contact, what exactly is going on the surfaces. And so I think a thing that's really exciting about this is things, your macro scale rheology is controlled both by the microstructure and also nanoscale things that are going on at the surface. And just sort of 2-second future perspectives in granular materials. We've seen here, this is a scenario where this ideas about jamming taken from the granular physics community were really instrumental in getting a handle on this sort of long-standing problem in the chemical engineering community, the shear thickening. And so I think that there's a lot to mine here in terms of tackling, so the things I've highlighted here is essentially all of chemical engineering, but I think there's, adding in, looking at these sort of really messy, there are progressively more messy systems that people deal with in industry, but asking, are there ways that you can take, take insights and ideas from granular physics to develop sort of unifying underlying principles that control these complex granular flows. So one quick example is the process of granulation. That is, when you're incorporating, so this becomes a really messy problem. You don't just have solids, liquids, you have solids, liquids, and air. You have to think about the air interface So it becomes a really nasty problem where you're moving above your random close packing, or at least above your maximum packing. But at least qualitatively, the phenomenology of this granulation procedure can be sort of captured very well by the sort of the two-branch structure that emerged from this friction-driven shear thickening. So thank you, and probably over, so I'll, yeah.
If you have any questions, you are free to ask.